Alright, had quite a bit of technical difficulties today. We've got new software, hardware, and nothing is working together. So we are going to take one, and that is going to be it. This is a new section, sensitivity analysis, to include in the course. We're going to be looking at the 3.3 types of examples, but we're going to add on some new things. So we're going to be finding ranges of values that the coefficients and the objective function can assume without changing the optimal solution. So in other words, not changing that ordered pair. And then we're going to be looking at something called shadow prices for a particular constraint, and then identifying constraints as binding or non-binding. So the big ideas here are some questions we're going to be asking are, by how much can we tweak that profit or cost per item sold without changing that optimal product mix? So maybe we can charge another $1 for a particular item and increase some profit some without changing our constraints. And then also, by how much does that increase our overall profit or decrease our overall cost? And what might be some economic benefits of increasing our constraints, our resources? Maybe we could increase our labor or materials or the amount of time we can spend producing our products on a machine. The first example, you've seen something similar on your homework in Chapter 3. And you're going to see something else like it in your group work for 3.4. So we've got Ace Novelty producing two types of souvenirs, type A and B. And we are going to stick to two-dimensional systems just for the sake of ease of graphing. Now we got the type A's result in a $1 profit for now. And type B's are resulting in a $1.20 profit each. And the type A's require 2 minutes on machine 1 and 1 minute on machine 2. Type B requires 1 minute on machine 1 and 3 on machine 2. And we've got 3 hours available on machine 1 and only 5 available on machine 2. So how many souvenirs of each type, so there's how we're going to define our variables, should Ace make to maximize its profit? So let's go ahead and write down that LPP. We got to have the word. So our goal, our objective is to maximize profit. And the type A's are giving me $1 each, so you can put a 1 in front of the X if you'd like. But then we've also got the type B's giving us $1.20 per souvenir. Now, we've got the constraints here of total time for machine 1. And you don't have to put these words by them, but they do tend to help. And remember, we want to keep our units consistent within each constraint. So for machine 1, we've got a maximum of 3 hours. So remember, that's got to be in minutes as well. So we got to have less than or equal to, let's see, 180 minutes. And then machine 2, we've got 5 hours. So that's going to be less than or equal to 300 minutes. Oops, it looks like a 4. All right, let me move this up a little bit. Okay, so if we look back in the paragraph, and this is where sometimes your highlighters can come in handy. So it does say that a type A requires 2 minutes on machine 1. But then it also says a type B requires 1 minute on machine 1. So my machine 1 equation is going to come from both types of souvenirs. So 2 minutes from every X and 1 minute from every Y. So 2X plus 1Y. And then we're going to have 1 minute from the type A's on machine 2, so that's 1X, and 3 minutes on machine 2 for every Y. So that's going to be plus 3Y. So let's use a separate color for that one. And I don't have my little orange guide here. So we had 5 hours available there and 3 hours available here. So that's where those numbers are coming from. And we can't forget those non-negative constraints. Okay, so you got to have that X greater than or equal to 0 and Y greater than or equal to 0. Alright, so we need to graph this. This is actually a 3.3 type of question, so you should be able to do this one on your own. Alright, so we need to label these so we can get some nice graphs going. So for number 1, we need an x-intercept and a y-intercept. So if you cover up the y to get the x, you'd have 2x is 180, which means that x is 90. So you'd have 90, 0, and for the y-intercept, cover up the y, you get y is 180. So we would have 0, 180. And then for the second graph, I guess I could do that just over here. We've got, if we cover up the x's, we got, or I'm sorry, cover up the y's, we got x is equal to 300. So for the x-intercepts, oops, 0. And then for the y-intercepts, covering up the x, we get 3y is equal to 300, which tells me that y is equal to 100. So I've got 0, 100. So it looks like maybe I can go by 90s on my grid. So over here, maybe 90 and then 180, and let's see, add 90 more, you get 270. Add 90 more, you'd have 360. So we could do the same thing up here. Alright, so there's really not a shortcut to doing these other than graphing. You do need to graph. So you got 300, which is maybe, oh, I don't know, maybe right here, 300, 0, and 0, 100. And that's the second graph, that's the orange one, so it might be helpful to color code those dots right there, so we remember where those came from. And if you've got a straight edge, that might help even more. And we also have those non-negative constraints. I usually have a red one over here, but I don't, so I'm going to use that bright green one here to remind us we are restricted in that first quadrant. So we still need a test point for that first graph, or the second graph actually, and that one was in orange. I need to highlight that. So let's go ahead and do our test point, and then we'll highlight. So we could choose 0, 0. And it turns out if you plug in 0, 0, and 0 makes me less than 300. And that is true. And if it's true, remember you shade toward. Okay? So we have this equation here, or this inequality now, is shading toward the 0, 0. So we need the second inequality. We've got the x-intercept of 90, 0, and then 0, 180. So again, you can go ahead and plot your segments, and you can choose a test point, again, of 0, 0, if you like, and plug this in, and certainly 0 and 0 is going to be less than or equal to 180. So that again is a true statement, so we're going to be shading toward the origin. So it's bounded in this little section here by the orange, and now this one is that blue line. And so down here on this end, we're bounded by the blue line. So if we're looking at our total shaded area, everything points inside this little piece right here. So we've got 4 corner points that we're going to have to check to see which one is going to do the job of maximizing. So 0, 0 typically isn't the one. It might be this one. Let's see. That's the 90, 100 from the, I should color code those as well. Those are the blue graph. So 90, 100, or 90, 0. And let's see, we've got 0, 90. No, 0, 100. I've been out this for several hours, and it's almost 6 o'clock in the morning, so things are a little tired at this point. Alright, so let's see, we need one more corner point. That's that intersection right there, and we can do an RREF to get the intersection of that system. So we got 2, 1, and 180. And then we've got 1, 3, and 300. And we can do RREF of that. So grab your calculator. And remember, we're just going to go into a matrix, and we're going to edit. And we're 2 by 3. So we got 2, 1, oops, 2, 1, and 180. And I got the 1, 3, and the 300, so I'm going to quit that since I have it in there. And I'm going to go to matrix, and this time math, RREF, and pull up matrix A. And there's my answer. So I've got 1, 0, 0, 1, 48, and 84. So that tells me that intersection point right there is going to be the 48, 84. But I still need to check, because if you remember from an example from last time, that particular point wasn't actually the one that did the maximizing. So we do need to check all of these corner points in our objective function. So if p is equal to x plus 1.2, or 1.20, doesn't matter y, I'm going to have 0 here. If I plug in 90, that's just going to affect the x. And if I plug in 100, that's just going to move that decimal 2 places over, so 120. And the 48 and the 84, if you plug that one in, I'll just save you some time here, that's going to be 148.8. If we're talking dollars, we would probably round that up with the 0 on the end. So anytime you're working through these, make sure you look back at the instructions and understand what it is you're trying to figure out. So the question asked, how many souvenirs, right? So X was representing the number of type A's, Y was representing the number of type B's. So the question is, once you figure this stuff out, is it asking for this information or this information? Well, how many souvenirs, that's what X and the Y represented. So for the first question, how many souvenirs, that means we want 48 of the type A, and then we want 84 of the type B. And oftentimes WebAssign will have you type this in as an ordered pair of 48, 84. So that's considered the optimal solution. So if we wanted the optimal value, that's referring to the maximum profit. So the optimal value would be equal to, since we're trying to maximize, would be that 148.80. So what if you own this company and you see that type A souvenirs just start flying off the shelves? So people really want these things and they are in high demand. What would you do if you own the company? Well, my guess is, being the smart students that you are, is you would probably increase their price. Because what's that going to do to your bottom line? Well, it's probably going to increase your profits. Now, you have to be careful with that sort of thing, though, because remember, you don't have an unlimited set of resources to produce an unlimited number of supplies. So sometimes you have those constraints that can't change. You have a certain amount of labor hours because you've got a budget you can pay people with, or you've got a certain machine that can only operate so many minutes per day, and those constraints can't change. So we're looking for what we can change that type A souvenir profit contribution to. So we want to kind of trap it between $2 amounts so that we can still keep that optimal solution of the 48 type A's and the 84 type B's, because that helps us keep those constraints in order. Now, we wouldn't want to look at the profit from type A and then go, okay, well, what happens if I make it $1.01 or $1.02 or $1.03? Because then you're going to have to solve hundreds of linear programming problems, and that would just take forever. So math can actually take the guesswork out of all this and figure it out for you. So I'm going to show you how to do that. Now, a picture down here is kind of show you what's going on with this. And so let me scoot this up a little bit. So of course it's got the constraints here. This is the constraint 1. So you'll notice the equation looks familiar from the last time. And this paragraph is just a repeat of those words in case you needed to refer back to it. And then this one is the constraint 2 that we had here. Now, this isoprofit line is the one that gives the P equals the 148.8, okay? So if we start playing around with these coefficients on our objective function P, that's going to change this isoprofit line, all right? Now, it turns out that if we go beyond this isoprofit line, that's going to change our optimal solution. And if we go beyond this isoprofit line, like up here, that's also going to change our optimal solution. So we need to stay within the boundaries of these two isoprofit lines. And the way we do that is we can compare the slopes with the slope of the objective function. In other words, what number is sitting in front of the x once everything is solved for y. And that's how we're going to do our comparisons. So we're going to take the P function, so this is from the previous page. And we have that P is equal to 1x plus 1.20y. Now, if we're interested in looking at the slope, what's in front of x, because, not just because it's the slope, but because we're focusing on type A souvenirs and x represented the type A's, we want to look at that coefficient in front of the x's. So that's how we're going to be looking at our comparisons of these slopes per se. So for this one, I would want to solve for y, because that's going to put it in the sort of slope-intercept form here. So we would want to subtract the ax over, and then we could divide by the 1.2. And remember, this is a multi-step fraction here, so you just got p over 1.2 minus the ax over 1.2, but that's just going to give me y equals, and you can separate it if you want to. If you took 119, I believe Miss Peary still refers to that as the mucus problem. But then you can clearly see what's sitting in front of that x, okay? So our goal here is to take what's sitting in front of that x, the negative a over 1.2, and we want to trap that in between the slopes of these two constraints. So my first constraint, if you look back at your problem on the previous page, we had 2x plus y is equal to 180. And if we solve that for y, we can just subtract the 2x. So on our second constraint, we have that x plus 3y is equal to 300. And if we solve that for y, we'd have to subtract the x over. This is a little bit more work. And then divide everything by 3. So this is going to give me y is equal to 100 minus 1/3 x. So by comparing the slopes of these two constraints, I can force my isoprofit line to fall in between these two. So I keep that optimal solution right there. So when you do these little compound inequalities, you always want to make sure your answers make sense. So you always want to put the smallest here and the largest here. And that smallest between negative 2 and negative 1/3 is going to be negative 2. And negative 1/3 is going to be the largest. So to solve, you want to get rid of the negative and the 1.2. So that's what you're going to multiply by, is negative 1.2. So if I multiply by negative, remember we reverse the sign of the inequality, reverse the direction. And if we multiply by negative 1.2, that's going to give me, let's see, we've got 2 times 1.2, which is 2.4. And it's positive because negative negative is positive. And then finally, we've got negative 1/3. Make sure you put that in parentheses if it's a fraction. Times the 1.2. And that I didn't multiply by negative here, but it is two negatives multiplied together. So that's actually equal to positive 0.4. So what we've just figured out is that, and we need to rewrite this properly because remember we always want to go smallest to largest, and when we multiply by that negative, they kind of switch directions here. So 0.4 is actually the smaller, and 2.4 is actually the larger. So we could say that the optimal solution of this is going to hold if the contribution to the profit lies between anywhere from 40 cents per item and $2.40. So which one do you think the company is going to choose? So if that A is going to be 2.4 now, so this A right here. So now if P is equal to now 2.4 times X, and we keep that Y fixed at $1.20. Well, let's see what's going to happen here. We'd have 2.4. We're going to keep the 48. And then if we've got 1.2, we're going to keep the 84. So this would give me a grand total of $2.16. So by how much did it increase? Well, before, so this is the new P. Yeah, so all I did is compute the new P, the old P, and then do the subtraction. So they know as long as they hold their price in between that 40 cents and 2.40 cents per type A souvenir, they're not going to have to solve every single LPP from $1 all the way up to $2.40. That would be very tedious to have to do. So part C is a different type of question. Here we have the profit. We're trying to find the contribution to the profit of a type A, making the type B held at $1.20. And we're given that the optimal profit will be $172.80. So we're still thinking about this idea of AX plus the 1.20Y. We just got some different variables to think about, play around with. So here, type B is held at 120. We still know, though, that we're keeping the 48.84 optimal mix. So X is still going to be 48. Y is still going to be 84. But now my profit is going to be defined as being 172.80. So that's just an algebra skill, really, working out through A. So we could subtract that 100.8. Not sure why I just drew a division sign. Like I said, a little bit tired working so late this morning. And we get 48A is 172, or is positive 72. And if you divide by 48, you're going to get that A is equal to 1.5. So the contribution to the profit of type A is going to need to be $1.50 per type A souvenir in order to maintain that optimal solution and make a profit of $172.80.